pi over a is first zero crossing. So pi over a is the first zero crossing. And then 2 pi over a. And what's the height of that? The height is, if it's like that, no, you know, when x is going to 0, this is like almost ax divided by ax, so get 1. The height is 1, and then 0 crossing pi over a. Okay? Height is 1, 0 crossing pi over, this is like your a. So, for c of ax, this is pi over. Okay, even function, yes, it is even. Oscillating function with decreasing amplitude, yes. It has unit peak at x equal to 0 and 0 crossing at, okay, it has integer multiples of pi for that. For this one is multiples of pi over a. Pi over a. If you have a sink of a. You don't need to memorize these things, right? I don't remember, I always calculate. Just knowing the definition helps you to know what's going on. Any question here? No? Now let's do this example. Fourier transform of GT looking like that. So do you recognize this gamma thing? It's a pulse. So it's a pulse signal T over tau. Let's look at how does it look like. I guess it was between minus tau and 2. So this is the pulse diagram for the work. So we have a pulse between minus tau over 2 and tau over 2 in the time domain. And I want to find the Fourier transform of that. What's the Fourier transform? Okay, very simple. We have a formula, integral of gt e to power e to minus j 2 pi ft dt. And then look at the pulse here between only minus tau over 2 and tau over 2. So that's going like this. Outside the range, the value is 0. So therefore, I can just write it from negative pi over 2 to pi over 2. And then exponential thing. So what happened to this one? Why it's not here?
Yeah, the constant value 1.
1, very good. So the whole thing here, and between this and this, the value was 1, right? So the whole thing here, I can, it's just the 1. Good. Okay, again, very simple integral. Just take the integral, replace the boundaries, and okay, so anybody recognizes someone this formula?
Euler's identity.
What's that?
Euler's identity. Euler.
Yeah, Euler, yeah. So what do I get?
Cosine theta.
I need a sign.
The whole thing like similar e to the power of negative j something, let's say some theta, minus e to the power of j dash. Okay. Just look at this. Is this familiar for you? So,
Is that equal to 2j sine theta?
oh, very good. Very
I
good.
didn't
Very good.
sign with the negative, now you apply a negative.
Yeah, you have a negative as well.
Apply a negative
So look at the sign. Yeah, thank you. Yeah. E to power j theta minus e minus j theta divided by 2j. Okay. So therefore, when you see these and then there's a negative sign, it's always related to this sign. So this is minus 2j sign of theta. Very good. Yeah, thanks for those that remember this. Right. And if I had a plus here, what would I get? Twice cosine. Right. It's just a rearrangement. If you multiply this sign by 2j, you're going to get that. And if you multiply the cosine plus. Again, it's very, very useful identities. Yeah. Okay, very good. So therefore, instead of this, I can say minus 2j sine of this theta or apple. You have phi f tau divided by 2, whatever it is. And then you have minus divided by minus j 2 pi f. So a lot of things just cancel each other. So it becomes the reciprocal form. So please just write this down. That instead of this, I write it as minus 2j sine. I have it here, minus 2j sine. This was this. And then when we simplify it, look at this. A sine function, pi f tau, divided by pi f. So it reminds me of a sinc function. Sine of something divided by that variable. Sine of some variable divided by that variable. Now, what's the variable here? Anyone can tell me?
So pi f, is that what you're asking for?
What's the variable? Like for example, when I'm looking at the sinc function sine of x, the variable is x. X is changed. So what's the variable here? What's changing here?
F.
F. Thank you. Remember, Fourier transform is all about finding what's the frequency component. So the variable is f. So my function is a function of f. What's going on? Different frequency. So my f is the variable. This is variable. Okay. Thank you. So therefore, just to make them like similar, I just multiply by tau here and then here. And then this is like a sinc function, right? Sine of something apple divided by apple. The sinc of apple. Okay.
Why is it multiplied by tau?
Because see here that my apple had a tau. Who asked the question? Oh, okay. So I'm adding. Okay. So here I had a tau. Okay. But my denominator didn't have a tau. So just to make them similar, look the same apple. So because you have sine of x divided by x, right? This is called sinc of x. So you see the same thing, apple, apple, apple. So now I was missing a tau here. So what I did, multiply my tau here and tau here. The same thing, right? Now they are the same. Now this is apple, this is apple. So that becomes a sinc of apple, then I have a tau here. Okay? Very good. So now we got a sinc function. And this is maybe one of the things that I remember from my signal analysis class 20 years ago. That when we have a pulse in time domain, in the frequency domain we have a sinc. Okay, in the time domain we have a pulse. In the frequency we have a sinc function. And we just proved it. Now look at the sinc function. So what we got was tau times sinc of that. Okay. And if you just do this as an exercise, to see how we get this 1 over tau here. So the first zero crossing is 1 over tau, and the amplitude is tau. See, we always said the amplitude was 1, remember? Here was 1. But because I had a tau here, so the amplitude has to be tau here. And then the first zero crossing is 1 over tau. Okay. So just the way to remember, this is a pulse of width. What's the width of this pulse? Tau. Okay, so it's a pulse, the duration is tau second. Okay, there's a pulse duration 1 over tau second. So when you look at the Fourier transform, it's a thing that the height is tau. The height is tau, and then the first zero crossing is 1 over tau. Okay, so I guess it makes sense. Now let's look at some physical intuitions again. Let's look at two different pulses. Let's say I have a two extreme. If I have a very short pulse, like this, let's say tau equals 1, versus a very weak pulse, what to call it, long pulse, tau is 10 or 100. So let's see what's the difference in the frequency domain. This is time, right? So in the time domain, I look at these two pulses and my eye can differentiate between them. This is a short pulse, 1 second, come and go. This one lasts for like 100 seconds. Okay? So let's take a Fourier transform and compare the Fourier transform. See how that difference is translated in the Fourier domain, frequency domain. Okay, we have this template, very simple template. The height is tau. Here the height is 1, and then 1 over tau is my first zero crossing. So this is how the GF look like in this case. For the second one, what's the height? 100. Okay, good. I wish I could say it. Let's get out here. Let's say this is 100. This is 100. So very, very tall. And then where is the first zero crossing? 1 over 100. So very nice. Okay, right. So now what's the interpretation? Which one has more higher frequencies? Top one. See, still look at like this frequency, but still you have some values, right? But for this one, already has died out. Look at here. So therefore, this one is like has more higher frequency. Has more higher frequency. Somehow makes sense. Why? This one was 0, shortly can go back. But this one was like constant for a long time, relatively. So more low frequencies here, and this is present here. See, this is low frequency. We have a lot of low frequencies. So lots of low frequencies. Not much high frequency. Versus here, you still have high frequency because my pulse was short. Yes.
So would it be like it has a lot more high frequencies for the or low frequencies for the second one?
This one has more low frequencies. Yes.
Because they kind of add up, and that's why the pulse is longer. Because then if you have lower frequencies, they would take away from that, or higher frequencies.
Well, the way that I look at it is that because see, this was constant, so you don't see a lot of variation for a long time. Okay, so it somehow introduces low frequencies. Like look at the DC at the extreme. If you have a DC signal, there's there's only DC at 0, and there's nothing else. That's why in impulse, so okay, so if you have a DC signal, DC, and so you have a voltage from negative infinity to infinity is always 5 volts. If you look at the frequency domain, it's only, it's a delta function, meaning that's only how you have DC, 0, nothing else. So this is like somehow between the DC and that one. So you have some changes. Because of this change, yes, you are going to see still this variation, this very small variations. But then the signal has been constant for a long time. And then again drops. That's how you have a lot of low frequencies. Okay, good. So I hope, yeah, so you can just see this intuition behind this formula. And again, something to remember. Pulse in this domain, sing in that domain. Pulse here, sing there. Okay, sure, method. And by the way, you have the homework and quiz of it. Yes, question.
Is the material that we didn't get to yet going to be on the quiz Wednesday?
And half the homework is from what we just talked about.
Oh yeah, so you have.
Any on the last time was something about duality principle?
Oh, it is? No, we haven't studied that. Okay, I'm gonna look at it. Yeah, if you haven't studied, there's nothing.